Okay, very good morning to all of you. We'll wait for at least 2-3 minutes more. Hope that we touch 100 again. Till then, in case you have doubts, please ask. Okay, are there any questions?
Hello, sir.
Yes, Triple.
Sir, in the example which you did in last class, that d by dx, like differentiation example,
Right?
sir, like above you have written that transformation matrix should be multiplied by input matrix, which is in column form,
Yes.
and the column of input should be multiplied by row of transformation matrix. No, you have done row column into column multiplication in the answer you have provided here downside.
Let me just open that up.
It is on page number 7.
Okay, once again.
Yes, this one, sir. Sir, can you just go above, like two more slides, number 5 or 6 maybe?
This one?
Yes. So here our input is AI, this AI column, and
Right.
C is the transformation matrix, right?
Yes.
So then AI is to AN should be multiplied by the row of this transformation matrix. And
Right. So C11, A1, C1 to A2, so on and so forth.
yes, and this example which you have done, we are multiplying column by column.
Column by column. Where?
Because sir, first input should be 1, and you d by dx of 1 you have written 0, all zeros, which is the
Right.
column.
Yes, so which is why this first column is all zeros.
But sir, we should be multiplying by first. Okay, sir. So then, should we not be multiplying by the first row because like row
No,
by
no,
column?
no, no. See, this d by dx of 1, I'm doing this in order to find this matrix.
Okay.
Okay, because I mean, how do I get the matrix? I think if you look at the recording, I did not write this matrix before we wrote these last two equations. So in order to find the matrix, if you look at this slide, what is the first column over here? C11, C21, etc. What are those? Those are the coefficients of TUI, right? As you can see over here,
Yes.
right? So if I want to find the first column, what should I do? I should first find TU1. Okay, what is U1 in this example? U1 is this first basis, which is constant polynomial 1. Then I will apply the transformation to this first basis. I get 0, right?
Yes.
Now, how do I write 0 as a linear combination of these bases? It's 0 into
Zeros.
etc. etc.
Yes.
So these four zeros are nothing but your
Okay.
C11, C21, C31, and C41. Right? You
Right.
can see here J varies, I remains the same. So it's ith column.
Right, sir.
Okay, so that's how you get your first column. Then in order to get the second column, TU2, U2 is x, right?
X.
The second basis. So d by dx of x is the constant polynomial 1. And I can write the constant polynomial as this particular linear combination.
Okay.
Is that okay?
Yes, sir. Got it.
Okay. Any other questions? Okay, if there are no more questions, let's get started. We saw the definition of invariant subspace in the last class, and we saw the advantage that it provides, right? If we have the decomposition of the vector space in terms of direct sum of invariant subspaces, then in the basis of these subspaces, right, the matrix representation becomes block diagonal. Okay, so as such, the concept of invariant subspace is important. Okay, towards the end of the last class, we saw this particular examples of invariant subspaces. Two more generic examples of invariant subspaces are the kernel or the null space of the transformation, as well as the range of any transformation. These two, right, are subspaces and they are always invariant. Is that okay? In null space, I think is easy, right? Any vector in the null space gets mapped to theta. Theta also is an element of the null space. So therefore, the null space is an invariant subspace. Similarly, range, okay, range of T is nothing but the set of all y's in U, and such that there exists an x in U with Tx equals y. Okay, so will y be an invariant? I mean, will this set be an invariant subspace? Right? What can we say about T of y, where y comes from the range of T? T of y by definition has to belong to the range of T, isn't it? Is it clear?
Yes, sir.
Okay, so that is why range of T will also be an invariant subspace. Okay, now let's look at specific examples of invariant subspaces or specific cases rather than examples. Okay, so we are going to look at eigenvectors as from the lens of an invariant subspace. Okay? So let V be a one-dimensional invariant subspace, okay, for a specific given linear operator T. Okay. So the only difference from the previous cases, we are specifying that this invariant subspace V is one-dimensional. So if it is one-dimensional, the entire subspace is nothing but a scalar multiple of a specific vector, right? All scalar multiples of a specific vector, which can be thought of as a basis of that one-dimensional subspace. So therefore, can write V as k times U. Okay, and U of course is the basis of V. Then let us pick any non-zero vector from this one-dimensional invariant subspace. Okay, since I'm picking a non-zero vector from V, I can write X as some scalar multiple of the basis U, and since X is non-zero and U is the basis, right, K surely is a non-zero scalar. Is that okay?
Yes, sir.
Okay, so then what can we say about Tx? Okay. If I apply T to X, since I already assume that V is an invariant subspace, Tx is also going to belong to the same subspace V, right? And therefore Tx has to be equal to possibly a different scalar times U. Okay, so some k1 times U. Okay, and then if I substitute X equals Ku in this equation, I'm going to get Tu equals K1 by Ku. There is no issue over here because K is non-zero, right? That is something we know. Okay. Now this K1 by K is also an element of the field, right? By definition. So instead of writing K1 by K, we'll write it as some lambda. Okay, and if I write this equation in this form, all of you hopefully recall that this is nothing but the definition of eigenvalue lambda associated with the eigenvector U. Is that okay?
Yes, sir.
Now the question is the choice of U unique?
No.
No. So what other U can you choose?
Sir, here U is vector of basis or any vector from V.
So for a one-dimensional subspace, what can a basis be?
Okay, yes, yeah, any vector apart from theta.
Exactly. Right. So Sarthak, you've already therefore answered my main question, right? Since the basis U is not unique, right? Any non-zero vector of this subspace V can be a basis. So therefore there is nothing unique about this U. Okay. So P into K times U, what would that be equal to? K into Tu by definition should be equal to K times lambda U. This would be equal to lambda into Ku. Okay, so that means if U is an eigenvector associated with eigenvalue lambda, and so is the vector K times U for any K which is not 0. Can anybody think about the reason why K should not be 0?
So then all the transformations would map to identity only.
No. Why? If K is 0, what happens? Ku becomes theta, right?
X becomes theta.
Yes.
Right. So then what is the problem? Why don't we call theta an eigenvector, or can we call theta an eigenvector?
And we cannot know what is the eigenvalue.
Cannot?
We cannot say, we cannot use an eigenvalue for that.
Exactly. Why? Because no matter what your linear transformation is, right? First of all, we know T will map theta to theta, right? So there is nothing specific about that choice. Okay, and you're also right where you say we cannot know lambda, right? This T theta is theta, so theta can be written as any scalar multiple of theta. Okay, so for these reasons, okay, whenever we talk about an eigenvector, by definition, it has to mean a non-zero vector. Okay, but then what we have just seen is if you have U as an eigenvector associated with a specific eigenvalue lambda, then any scalar multiple apart from 0 is also an eigenvector associated with lambda. Okay, which also means if there is one eigenvector, then there are infinitely many eigenvectors, assuming we have an infinite field, of course. Okay, so then let us try to see how do we find eigenvalues, okay, and eigenvectors. So this is something that you may already be knowing, right? Can anybody give me an answer to that?
Characteristic equation.
Characteristic equation, or it's also an equation, but then what do we do with the characteristic equation?
Find the values for lambda, possible values.
Okay, there's one small difficulty there. So what is T over here? And what is it that you mean by characteristic equation?
T minus lambda equal to
T minus lambda. Does that make sense?
lambda
Lambda
I.
is lambda. T minus lambda I. Then
Equal to 0. T minus lambda equal to 0.
Theta penalty.
so T minus lambda I equals 0. That I think you can see directly from here, right? This is the same as saying T minus lambda U equals theta. Then you can write this as T minus lambda times the identity operator Pu equals theta. Then Okay, so by the way, be careful. T minus lambda u is equal to theta, not 0. Yes, then what do we do with this?
U cannot be theta, so T minus lambda should be theta.
U cannot be theta, so T minus lambda I must be theta. Is that right?
Like, all columns are theta.
No, T minus lambda I cannot be theta, right? T minus lambda I is a transformation,
That means
whereas theta is a vector. Okay, so in principle, both of them belong to different vector spaces.
Sir, we need to find the transformation such that u is mapped to theta.
No, just a minute. So T is a given transformation, right? So that is not a variable.
Sir,
And
lambda can be variable because we need to find
yes,
lambda. That's why.
but so U also is unknown, right? So are you going to try this for each and every U and see which lambda is going to work out? Or the other way around? You're going to fix lambda and then find U and then change lambda and then again find U. How are you going to proceed with this?
Sir, lambda will be fixed and I
So
will
how will
find.
you fix lambda?
So u can be theta, so we can say that T minus lambda should only be equal to theta.
No, but see, T minus lambda I is a transformation, right?
Means
It belongs.
determinant.
What do you mean by determinant of this and why? I mean, I guess all of us can assume we know what does determinant of a square matrix mean. But is T a matrix? Okay, so this is what we all agree with, I hope. Okay, please never say that this implies T minus lambda I equals theta. Okay, this is horribly wrong. These both of them are not elements of a field. Okay, T minus lambda I and U, they don't belong to some field. If they were
We have to
belonging to some field, then if the multiplication of this is 0, then you can sort of say one of them has to be 0. Okay, these belong to two completely different vector spaces, by the way. Okay, so this is not right. Moreover, it is also not right that if u is not theta, this has to be the 0 transformation. Maybe I'll write it in this way. This also is not right. Right? What this basically means is u is what sort of a vector? Is non-zero, of course. Once again, Kush, could you?
It's one dimensional. It's one dimensional.
No. See, u is not a subspace. U is just a vector. But what can you see from this equation?
It's a inverse T minus lambda I is the
Oh.
inverse.
Sir, u belongs to null space of
Good.
T
Null
minus lambda
space
I.
of T minus lambda I. So in fact, Kush, if u is a non-zero vector in the null space of this operator, do you think T minus lambda I can be invertible? Okay, let me make it more easy for you. T minus lambda I will map theta to what vector? Quick, I don't think I asked a particularly difficult question.
Theta.
And we also know that t minus lambda is the same transformation or operator maps u to theta, and we know that u is not theta. What does both these equations imply?
T minus lambda I theta.
No, t minus lambda I
Not invert.
is not invertible. Why? Invertible, I mean, if something is not invertible, that means it cannot be bijective. So why is this not bijective?
It is not 1-1.
Yes.
Right? It's not 1-1. So it's not invertible. Then this is not invertible, then what can we do? I'm sure you guys have found eigenvectors, eigenvalues, right? Yes or no?
Sir, can we do it like
Not invertible, then determinant must be 0.
Exactly. If this is not invertible, but there is one difficulty there. Was that Purav who answered this?
Sir, Vihar.
Sorry, once again. I think I
Yes, sir.
repeated the same mistake
No problem.
again.
Yes.
Right. So Vihar, if this is not invertible, can I say determinant of this is 0?
Yes, sir.
Anybody else would like to comment on this? Determinant is defined for what?
Only for square
Square
matrix.
matrix.
Only for square.
Square matrices. Is this a square matrix?
No, not
Why?
necessarily. Not necessarily. It hasn't been specified anywhere.
What does this mean?
Yes, sir. Actually, it's because linear operator.
So T is from U to U. So the domain and
Okay,
codomain are...
sorry, sir. Sorry. My mistake. Sorry, sir.
No. It's nothing to be sorry, but are you sure T minus lambda I is a square matrix?
Sir, it has to be because I is there, which is a square matrix.
No, but what is I?
I means identity matrix, and you.
No. Did I say that I is an identity matrix? What is I? I is a linear operator. It's called the identity operator. It's defined in this way. For all U in capital U, I maps U to U. Does that mean I is the identity matrix?
No, sir.
So then what can we say about T minus lambda I? Is it a square matrix? It's not a square matrix necessarily, right? Because it depends on what sort of vector space you are given with. Do you see that? So for example, U could be, I don't know, polynomials of degree at most 3. So U is a 4-dimensional vector space, but T is not necessarily a matrix, right? For example, in the previous class, we saw this differentiation on polynomials. Differentiation by itself is not a matrix, right?
Yes, sir.
But since U is assumed to be finite dimensional, with respect to a particular basis, you will have a matrix representation of T. And that matrix has to be square. Does that make sense?
Yes.
If T is square, how can be T minus lambda I defined? If lambda I is not square.
Just a minute. So the T be a basis of U. I'm saying is TBB will always be a square matrix. Okay. Dimension equals it. Yes. There's some question.
Like how is T minus lambda I defined if I is not square and T is square matrix?
No. See, T is not a square matrix. That's what I'm saying. T is a linear operator.
Okay.
Okay. Lambda is just a scalar. I is also a linear operator. Okay. So therefore, T minus lambda I is also a linear operator. Is that okay? If it is, now there's just one question. What can we say about this matrix minus lambda in? Okay, here in denotes the identity matrix. What can we say about this matrix? Is it invertible or not?
No, sir.
Why?
Because determinant is 0.
Now, how do you know determinant is 0?
Because no, no, no. Sir.
Not always.
Not always in the sense. So see, let us say T minus lambda I is not invertible, right? So lambda is such a value so that the linear operator T minus lambda I is not invertible. Then what can we say about this matrix?
So this is also not invertible because it is just a representation of that linear operator.
Exactly. See, if the matrix representation and of the linear operator and the linear operator itself, right? They have to be, the representation has to be faithful to the original entity, isn't it? We don't call representation just for the sake of calling it, right? Representation means it has to have the same characteristics of the original operator. So if this is invertible, right, then so is T minus lambda I, right? In the sense that, and vice versa, if T minus lambda I u is theta, then TBB minus lambda in multiplied to the representation of u in this basis, this has to be the n-dimensional zero vector. Do you see why this must be true?
Yes, sir.
Okay, so representations sort of have the same feature. You cannot just arbitrarily have matrices. So then how can then I can now talk of determinants, right? Because now I have a square matrix. So what can we say about this determinant?
0.
0. Good. Now I think we have connected the dots. Right? This is in. Okay, so there is an n missing. Remember, this I and this I are different. Okay, here this is the n by n identity matrix. Okay, remember the identity operator in any basis will have a matrix representation that is just the identity matrix. Okay, so it's something that I already assumed. I hope it is okay. So now if this is 0, now the question is, if I do not know lambda and u, how do I go about finding lambdas and u's?
From this equation, we'll get lambda.
Exactly. So see, if I'm given a linear operator, first of all, I should choose a basis of my vector space. Then I should obtain the matrix representation of my linear operator. Then I should find basically lambda such that determinant of t beta beta minus lambda in is 0. Okay. So therefore, I hope you see this thing. What will this be? This will be a polynomial, right? Okay, so this will be a polynomial in X of what degree?
Sir, 1.
Why would it be 1?
Degree n.
N.
Degree n. Okay, because you have n diagonal elements, so you can multiply them out. You will have sort of degree which will be n. Okay, this will be denoted by C subscript the linear operator t in the argument x. Okay, and we are interested in finding the roots of this polynomial. Okay, this is exactly giving us that. Okay, so the eigenvalues of my linear operator t are roots of this polynomial. This should be Cx, sorry for the change in notation. And then the eigenvector is nothing but a non-zero vector belonging to this particular null space. Okay, and also remember, how do I find this? I know that if this is the case, then this also has to happen. And vice versa. Okay, so you can again see, in order to find eigenvectors, you will have to solve a linear system of equations, and in this case it will be the homogeneous system of equations. Questions here?
So how the degree of this polynomial is n?
How? Okay. Okay, maybe I can give you examples. Would that be okay?
Yes, sir.
So let's say I have a 2 by 2 matrix, just randomly 1 minus 2. Let's say. Right? What would be A minus xi? What matrix would this be?
Two minus x, 3, 1 minus 2 minus x.
Determinant A minus xi. Right, so you can see this is quadratic.
Yes, I seen it now, sir. I was thinking of the degree of polynomials in the matrix.
Acha, okay. Right, so that also tells you how many eigenvalues can we have?
Maximum n.
Good. Maximum n. Okay. And how many eigenvectors? So this is a sort of a loaded question, right? If I literally take this question, then I've already answered this. Right? If we just saw in the previous slide on sort of looking at eigenvectors from an invariant subspace point of view, if there is one eigenvector, then
There are infinitely many.
Infinite.
Infinitely many, right? So that in that sense, this question, if taken literally, doesn't make sense. But since we know already that if there is one eigenvector, then there are infinitely many eigenvectors. What this question implicitly means is how many linearly independent eigenvectors can I have? Probably associated with different eigenvalues.
Also in maximum.
Maximum n. Good. Okay. You cannot have more than n because your vector space U is n dimensional. So there cannot be more than n linearly independent vectors. Forget eigenvectors. Is this clear to everyone? Just a new term. So this polynomial C of t is what is called the characteristic polynomial of t. Okay, now there is just I think one more question here. So we saw that how are we going to find eigenvalues? We are going to find eigenvalues of a linear operator t by first choosing a basis, obtaining its matrix representation, and then finding this characteristic polynomial. So the obvious question is, does the eigenvalue depend on the choice of basis? If instead of basis beta, if I choose alpha, will I get different eigenvalues?
Yes, sir.
Yes, sir.
Right. So, and then does that make sense? I mean, can I then really say that lambda is an eigenvalue of the linear operator T? If it is changing with this matrix, then I should really be saying that eigenvalues, I mean, lambda is an eigenvalue of this matrix, not of the original linear transformation T, isn't it? Right? Do you see an issue here? Because if it changes with beta, then this lambda is associated with this matrix, not with the original T, isn't it? Yes or no? I mean, is this question understood?
Yes, sir.
Yes, sir. But in a particular representation for a particular basis, we can also get the representation in another basis alpha. Like,
So that is right. But will, if so, that's my question. If lambda is an eigenvalue of T beta beta, right? And if instead of T beta beta, I map it, I mean, if I use this matrix T alpha alpha, will lambda be an eigenvalue of T alpha alpha also? If not, then we cannot really call lambda an eigenvalue of T, isn't it? Okay. Issue is clear. Maybe the answer is not, but is the issue understood to everyone?
Yes, sir.
yes.
Okay. So now let us see what happens. What is the relation between T alpha alpha and T beta beta?
N beta alpha, T beta beta.
Sorry.
N,
So there is a, these are similar matrices, right?
so
There
S,
is
S inverse.
exactly S T beta beta S inverse. There will be an invertible matrix S such that this holds true. Agree? So then I can just use this over here. Okay. Then I can also write it in this way. then I can also write it this way. Yes?
Yes.
Now is a well-known property of determinants. So if A, B, C are three matrices and whose matrix multiplication is compatible. So let's for now assume they are all square matrices of size n. Okay, then determinant of ABC is also equal to determinant of CAB, which is also equal to determinant of BCA. In other words, determinants are invariant to cyclic permutations. Okay, this is not only true for 3, but any number of matrices. Okay, but remember, they are not invariant to any arbitrary permutation. Okay, they are invariant only to cyclic permutations. Okay, so if, of course, you may not be aware of this, but for now, just assume this is the case. In that sense, what will we get here? What does that imply?
Same determinant.
Same lambda.
Exactly, right? So if lambda is an eigenvalue that you have computed through a particular matrix representation, it does not really matter what is the basis you have chosen. That is a crucial property, right? Otherwise, why would we call an eigenvalue of the linear operator? Right? So this is a crucial information that is required to make this a sound sort of derivation and concept. Okay, so it doesn't really matter what basis you choose in order to obtain the matrix representation. Okay, the determinant will remain the same. So the characteristic polynomial remains the same, and therefore the eigenvalues always remain the same. Okay.
Sir, I think determinant of AB equals to determinant of A into determinant of B. So it could be any permutation.
No, it's not any permutation.
So all metrics have same size, yeah, right?
Yes.
Then I have seen this formula: determinant of AB equal to determinant of A.
For two matrices, the cyclic permutation is the only non-identity permutation, right?
So can't we say that AB as AB as whole matrix and then C? So determinant of
Try it out. Try it out. I think,
okay.
right.
Okay.
And yeah, in case you sort of are able to show that it is invariant to any permutation, I would be happy to see it. Okay, and I will admit it if I'm wrong. So please let me know.
Yes.
To the best of my knowledge, it is invariant only to cyclic permutation. Okay, so that apart, I hope this is now clear, and I hope it is now making much more sense, right? Eigenvalues and eigenvectors of a linear transformation, sorry, linear operator. Okay. Okay, let's quickly look at a couple of examples. So R theta is the rotation transformation on R2 that we previously saw. Can we quickly find its eigenvalues and eigenvectors? And we are sort of running out of time, so please help me out quickly doing the computations. So
Before I get black eigenvalue.
Once again,
Eigenvalue will be of the sum for I theta.
that is not right. I'll tell you why. But before, I mean, let us take the entire class with us. So can somebody give me a choice of basis?
1001.
Right, let's not make it more complicated. And r theta in this space is what would it be? We already did
Cos
this.
theta, sin theta, minus sin theta, cos theta.
R theta BB minus XI2. What would be the matrix? Cos theta minus X minus sin theta, cos theta minus X. What is the determinant? Cos theta minus X squared plus sin theta squared, right?
Yes, sir.
Which is equal to cos theta square plus sin theta square is 1 plus x squared, or let me write it in the increasing order of degree. X cos theta and plus x squared. And so what are the roots? So what are the eigenvalues basically? Quick, what are the roots? Plus or minus b, right? You guys should be more, more efficient and faster than me. 2 cos theta, that's minus b, plus or minus square root b square. So 4 cos theta square, square minus 4ac, minus 4 by 2a, so 2. You can cancel out the 2's everywhere. What will you get?
Cos theta plus or minus root over square.
Iota sin theta.
Sin theta, that's it, right? So this is, as I think Raj pointed out, this is e raised to plus or minus I theta. These are the roots, right? Is everybody on the same page?
Yes, sir.
Yes.
Are these roots eigenvalues? You may think, I mean, what a stupid question. Just defined eigenvalues as roots. And now I'm asking, are these roots eigenvalues? Now, to look carefully at the definition of eigenvalues and eigenvectors, right? We started out with these invariant subspaces, KU, right? So an eigenvector has to be coming from the same space and it has to go to the same space, right? In other words, if U belongs to V, lambda U also should belong to V. Yes or no?
Yes.
Yes.
Yes, sir.
Now, do you think this is right here?
No, it will be complex.
Exactly. R theta is an operator that we have assumed is defined from R2 to R2. So e to the power I theta cannot be an eigenvalue unless, of course, theta is 0 or pi. Okay, so this is the important example. Unless theta is 0 or pi, e to the power plus or minus I theta are not eigenvalues of r theta considered as linear operator on R2. Please remember. In other words, in general, the eigenvalues have to What can you say about this? Eigenvalues have to belong to fill in the blank.
Field.
Plus minus 1.
Field.
The field of the vector space.
Exactly. Right? Because once it belongs to field, we know lambda into u also is an element of the same vector space. But if lambda is not from that field, then lambda u is not necessarily a vector in that vector space. Okay, so this is important. And for this example, it means r theta does not have any eigenvalue. And this should not be a surprise, because when we intuitively understand what rotation does, right, on the xy plane. R2 is nothing but the xy plane. What does this do? If I give a vector to it, it rotates by an angle theta. What is eigenvector and eigenvalue saying? Whatever was the input, the output is aligned with it. If you think of the rotation, right, there cannot be any vector which is aligned to itself before and after the rotation, isn't it? So we should not have expected any eigenvalues or eigenvectors to begin with. Right? Here sort of just went along mechanically without giving it a thought. Okay? But on the other hand, if I now consider the same transformation from and to C2, then the eigenvalues will be e raised to plus or minus I theta, right? Just for the sake of it, let us find out the eigenvectors, right? So that we have one example done throughout. How do I find the eigenvectors? So r theta bb was cos theta minus sin theta cos, sin theta cos theta. So r theta bb minus lambda I. Okay, so minus e raised to I theta. Xy should be equal to what? 0, right? I want to find the vectors, non-zero vectors in the null space of this matrix, right? So what is x and y? Solve for x and y. It's just a 2 by 2 system. Help me out quickly because we are sort of way behind the schedule. Or can I assume you will solve it now?
Yes, sir.
So fill in the
1
blank.
J,
Sorry?
1 and J.
1 and let's say I. Let us stick to
Ah.
same notation. Wait, 1 and I. Good. And how about the eigenvector for e raised to minus I theta? It is 1 minus I, if I'm not mistaken.
Yes, it's 1 minus I.
Okay, now let's see what happens if I do this. Cos theta minus sine theta, sine theta, cos theta into 1i, 1 minus I. What will I get? What would be the first column?
E
E
power minus I theta.
No. To the power I theta and I e to the power I theta. And similarly, the second one would be e to the power minus I theta and minus I e to the power minus I theta. This, I mean, if your computations are right, then these computations have to be right. Because what is the first column? Is this matrix times this first vector. What did we know about the first vector? It's an eigenvector corresponding to what eigenvalue? E to the power I theta, right? So the first column has to be lambda times the same vector, isn't it? And lambda was e to the power I theta, which is why I could just directly write it this way.
The column should be interchanged.
Column should be interchanged by
Here in this first, the first element in first column is e power minus I. It should be e power minus I theta.
no
Cos
why?
theta minus I sin theta.
No, then there is some mistake in this eigenvector computation.
They are just like reverse.
So you're saying the eigenvector corresponding to e to the power I theta is 1 minus I.
Yes, sir. In this last matrix equation, if you compute manually, then we're getting reverse columns.
Okay. So as I said, I assumed you guys did these computations right. I haven't done them myself. Okay, so then it should be this, 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 and this. Now is it right?
Yes.
Okay. So this right hand side matrix, I can rewrite it in this way also. 1i, 1 minus I times e raised to minus I theta, e raised to I theta 0, 0. Right? This is just a scalar multiple of the first column and this scalar multiple of the second column. That is this matrix. I denote this matrix as some capital E. This is also the same as E. What is this matrix? What does it look like? It's a diagonal matrix, right? Containing its eigenvalues on the diagonal. So let's call it capital lambda. What we have is this. Into E is equal to E into lambda, or in other words, lambda is E inverse R theta BB. So what is the conclusion? Remember when we started out with this matrix representation of linear operators, we said that if I really want to understand what that matrix is or what that linear transformation is doing, I would always prefer a basis which is going to give me a diagonal matrix. Is that right?
Sir, could you repeat it?
So when we saw that the matrix representation of a linear operator depends on what is the basis you have chosen, right? And we said that if I want to understand what that linear operator is doing intuitively, then it is always easier to understand the matrix which is diagonal.
Yes, sir.
Right? And here is exactly that example. We have chosen a basis such that in that basis, I get a diagonal matrix representation. What is this lambda? Lambda is nothing but r theta in the basis E, let's say. Yes or no? So then, can you sort of complete the circle? What sort of basis should I choose if I insist on having a diagonal matrix representation of the linear operator in that basis? What sort of basis?
Bases whose columns are the eigen values of.
No, not eigenvalues.
Sorry, eigenvectors.
Exactly. That is the important conclusion. So if a diagonal matrix representation is preferred, we need what is called an eigenbasis of the linear operator. What I mean by eigenbasis is that the basis of the vector space is such that every vector of my basis is an eigenvector of the given linear operator. Because let's say A is an n by n matrix, which could represent the linear transformation in any other basis as well. And let us say we have E1 to En, which is an eigenbasis of P. Okay, in the sense that E1 to En are n linearly independent vectors, and each of them is an eigenvector of my matrix A. In that case, if I have this matrix A and I multiply it to a matrix whose columns are its eigenvectors, by definition, I'm going to get this matrix. Right? The first column is going to be A into E1, but A into E1 is nothing but lambda 1 E1. Second column is going to be A E2, which is nothing but lambda 2 E2, and so on and so forth. The last column is going to be lambda n En. This matrix itself can be written as a product of this matrix into this diagonal matrix whose diagonal entries are nothing but the eigenvalues. Okay, so in principle, A into E is equal to E into the matrix lambda, which is diagonal. From that, lambda is equal to E inverse AE. Clear? So, I don't know, is it clear? Does it make sense?
Yes, sir.
So now the question is, if I give you any linear operator, is it guaranteed that I will have an eigenbasis?
No.
No, right? So that is the difficulty here. So for example, I'll give you a very trivial example. It's A be this matrix 1, 1, 1, 0. Can you find its eigenvalues and eigenvectors? A minus lambda I2 or x I2. Let me be consistent with my notations. This would be 1 minus x, 1, 0, 1 minus x. What is the determinant of this? 1 minus x squared. So what are the eigenvalues?
So x is equal to 1.
1. Only one eigenvalue, right? Okay, remember, even though the number of eigenvalue is less than n, you can still have n linearly independent eigenvectors. I'll give you an example of that soon. Okay, for this eigenvalue, what are the eigenvectors? A minus 1 times I2. What is that matrix? Quick, don't think it's difficult to see. 0, 0,
1 0.
1, 0. What is the null space of this matrix?
K0.
No. How can it be K0? I mean, K0 means the vector 0. That, of course, is in the null space. Is there any other vector? How about this? If this matrix is multiplied to 1, comma 0, what will happen?
Will give 0.
Right? So any scalar multiple of the vector 1, 0 is in the null space. So what is, can you give me the eigenvector then? Has to be 1,
0.
But you can see there is only one linearly independent eigenvector, right? There is nothing else you can do about it. Which implies A is not diagonalizable. Because there is no eigenbasis of this. So maybe I'll finish this discussion by giving you this example that I had stated, that can we have a matrix which has fewer than n eigenvalues but still n independent eigenvectors? And I'm sort of going to cheat, you can say that. How about this matrix? What are the eigenvalues?
One only.
Only one. Eigenvectors? Or in other words, let's first find the null space of I2 minus 1 times I2. What is I2 minus I2? That's 0. So what is the null space of the 0 matrix?
So the
R
whole
square.
vector space.
R2. So can you give me an eigenbasis? I mean entire R2, so all you have to do is to choose two linearly independent vectors.
1 0 and 0 1.
Exactly. This could be an eigenbasis. Yes, so as I said, you can have fewer number of eigenvalues, but still enough number of linearly independent eigenvectors. I will finish by stating this result here. Okay, so it's important to know when will we have enough eigenvectors. Okay, in general, there is no guarantee that the particular matrix is going to have enough number of eigenvectors. But one result that will help is this. So if I have m distinct eigenvalues, then for each eigenvalue I am at least going to get one eigenvector. Okay, because that comes by the determinant. Because lambda is where that determinant goes to 0. That means that matrix is not going to be invertible. That means there is going to be a non-zero vector in the null space, which means that that non-zero vector in the null space is going to be an eigenvector. Okay, so there are going to be at least these m eigenvectors. These m eigenvectors are guaranteed to be linearly independent. Okay, that is a result that I think we will maybe take up in the tutorial on Saturday. Okay, but for now, just assume this. And with this, I think we don't have enough room to have a more detailed discussion on eigenvectors and eigenvalues, at least for now. On Friday, we'll start with a new topic, which is inner products and norms, which I think will be the last topic of this course. Okay, but for which we'll need at least 2 more classes, if not 3. Okay, so yeah, thank you, and hope to see you guys on Friday.
Sir,
Yes.
sir, I had a doubt relating the project. So,
Okay. So just wait. I mean, others, you are free to leave. In case you have specific doubts, you can stay. Okay. Just stop the recording.